Okay, so exam 3, number 2. Okay, so you have a vector that's like this, and it makes an angle with the vertical of 40 degrees. And for part A, you have a coordinate system with the y-axis this way and the x-axis this way. And I drew it this way because you put the tail of the vector at the origin of the coordinate system. So this is x, this is y. And so the angle we want goes from the positive x-axis to the vector. So that's 90 plus 40, so 130. So theta is 130. And then for the second one, so the vector stays the same direction, but this time the coordinate system has the y-axis this way. That is a very crude coordinate system. Okay, and the x-axis this way. And we still know that it's 40 degrees from the vertical to the vector. So this is still 40 degrees. And now that 40-degree angle is the angle that we want. So theta is just equal to 40 in this case. Any questions about that one? Or any other questions on the test right now? Yep. Yeah. Okay, so number 1. So ball's thrown straight up into the air with a speed of 20 miles per hour. So if you're drawing what's happening, here's the ground. And it starts at a height of 3 feet and then goes straight up and straight back down. So this distance is 3 feet. And if you convert that, I think that's 0.914 meters. And it's thrown with an initial speed of 20 miles per hour. 20 miles per hour is 8.94 meters per second. So, I pretty much always put my 0 on the ground, my positive direction up. So here's the 0. Yeah. Let's see what I gave you. Okay, so 3 feet. And it gives you that 1 meter is 3.281 feet. So 3 feet, 3 divided by 3.281 is 0.914. So you can use the equation. The first thing it asks you for is the height of the ball at its highest point. So you can use this equation, 2a times the quantity. Yep. Okay, yeah. I remember actually grading that, yeah. A very small number of miles. That's fine, yeah. I just did that because that's what I'm used to working in, but you could do it in miles too. You just have to be sure that you convert everything else into units that are compatible. I think that's all that went wrong with that. Um, so you'd have to, so if you're going to do everything in miles and hours, you need to convert the acceleration of 9.81 meters per second squared into miles per hour squared, that kind of stuff. That's true. I guess that is why. Yeah. I just feel comfortable here. Okay, so 2a times the quantity pf minus pi is equal to vf squared minus vi squared. So that's 2 times negative 9.81 times the quantity. We're trying to find pf minus 0.914 is equal to, at the highest point, vf is 0, minus 8.94 squared, and you get, in meters, you get an answer of, do I remember that? No. But in 4.99 meters, okay, that sounds familiar. So PF is equal to 4.99 meters. And then you have to convert that to miles. So 4.99 meters. I don't know if I gave an easy way to do that. I didn't. Well, I know, so 1609.344 meters is 1 mile, and that converts to, what's the answer? Yeah, what is it? 3.1 times 10 to the minus third miles. So that's A. And then for part B, how long does it take to hit the ground? You have to choose a new time final, and then you can use the PF equals PI equation and calculate time. Any other questions on the test? Yes. Oh, 3B. Yes. I don't think anyone did 3B all the way right. I gave a couple people 1 point out of 2. That pretty much was nasty. Okay, so 3. 3A isn't, that's more reasonable. Okay, so an object is launched. So let me draw what's happening first. Okay, so an object is launched from a height of 4 meters at an angle of 10 degrees below horizontal. So that's the starting angle. And so it's going to start out like that and then follow a parabolic path down to the ground. And what did I say? 10 meters per second, I think. So at initial speed is 10 meters per second. So time equals 0 is going to be when it's launched. Time final is when it hits the ground. The coordinate system I'm going to put on the ground beneath where it's launched from. And so that means v sub I is the velocity of the object at the instant it's launched. So v sub I is 10 times cosine of 350. You can use negative 10 degrees. 10 times sine 350. And that is 9.85 negative 1.74. If you calculated that wrong, your calculator was probably in radians. And so now we're looking for how long does it take to hit the ground. I'll write out what we know. Bless you. What we want. So do we know time final? No, that's what we're looking for. The acceleration vector is 0, negative 9.81. The initial position is 0, 4. The final position, we don't know how far horizontally it goes, but we know that PFY is 0. And then we just calculated the initial velocity. That's 9.85, negative 1.74. And then we don't know V final. And the equation that'll work with this is PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0 is equal to 4 minus 1.74 PF minus 4.905 TF squared. And the answer is, so you pretty much have to use the quadratic formula to solve that. TF is equal to 0.743 seconds. And it's pretty easy to choose which one in this case because one's positive and one's negative. And then the hard one, the credit one, that I didn't decide was extra credit until I watched you all's faces as you were working on it. Actually, I think I started working through the problems also, and when I got to that one, I was like, oh hell no. So okay, let's go through that. Okay, so we'll keep time equals 0 and time final meaning the same thing. So this time, V initial is, so what do we know about that? Well, we still know the angle that it's launched from. So the angle is still, 350 or negative 10 degrees, but we don't know the speed. I'm going to call the speed time equals 0. I'm going to call that capital V. And so then the velocity vector is capital V times cosine of 350, capital V times sine of 350. And so that gives you 0.985 V and negative 0.174 V. And then we'll write out what we know and what we want. Okay, so time final, we don't know. Time final is going to be similar, not the same as it was in part A. So a few people just used the time from part A as your T final here. It gave you sort of a ballpark answer. But we don't really know what it is because if you launch it faster, in this case, it's going to hit the ground a little sooner. We don't want that necessarily if we don't have to solve for it. We still know A is 0, negative 9.81. We still know P initial is 0, 4. P final, we only know the Y value of P final, and that's equal to 0. What we're trying to find is PFX. The initial velocity, we know it if we know that speed. So once we find, if we can find that speed, we know this. So I'm going to write that here, and it's equal to 0.985 v negative 0.174 v, and we don't know the final velocity. So is there an equation that lets us solve for PFX? No. And so nothing works. And so we're going to do what we usually do, and that's solve for time final. That's the intermediate variable we normally use in a two-dimensional problem. Look for time final. So the equation that we're going to use is PFY is equal to PIY plus VIY PF plus 1/2 AY PF squared. And that says 0 is equal to 4 minus 0.174 V TF minus 4.905 TF squared. That's one that works. You could use the quadratic formula to solve that. I think this one also works. PFX is equal to PIX plus VIX PF plus 1/2 AX TF squared. So this says, so PFX is what we're looking for. And that's equal to 0 plus okay, so VIX is capital V times 0.985 times TF, and then this is equal to 0. Okay, so what are we going to do with that? I guess we just have to solve this one, even though we don't know what V is yet. So we're going to have to come up with an expression in terms of V. For T, I don't remember because I got it in terms of V, I think. So what you have to do is you have to find a pair of equations that let you solve for TF and V. Um, I feel like, well, oh, I know. Okay. So, okay, wait. So I explained this problem wrong. That's why this is confusing. Okay, so we're not looking for PFX. We're given that it's 5 meters. Okay. So we are looking for, we want that value of V. And we know that PF is 0.5. Okay, that makes more sense. And so we have this equation. We know this is true. Take the one with the value subbed in. So we know this equation is true, but it has two unknowns, so we can't solve for it. We also know that this equation is true. This should be 5. So now you can rearrange this one. So 5 is equal to 0.985 VTF. But now you have this system of two equations for two variables, V and TF, and you can solve it. I think the easiest way to do it is equation 2 star says TF is equal to is that what, yeah. So TF is equal to 5 divided by 0.985 V. What's 5 divided by 0.985? 5 point. 5.076, and that's over V. Okay. And now that we have that, we can substitute it into equation 1 star. So equation star says zero is equal to 4 minus 0.174 times 5.076, and the two V's cancel, and you have TF. Oh no, we substituted in there, so there's no TF there. Minus 4.905 TF squared. And so what's 0.174 times 5.76? What is it? 0.88. So 4.905 TF squared is equal to 4 minus 0.88, so 3.12. And then you can solve for TF and then solve for V. I guess if I would have substituted the other direction, I would have gotten V right away. But anyways, that's, I mean, that's way, like when I wrote that problem, that was not what I was picturing you having to do. So I'm sorry about that. That's pretty nasty. But let's solve it. So TF is equal to, what do you get here? 0, okay, 0.797. It should be 6, okay, be like a little smaller than what we got in part A, because you're throwing it a little faster, so it's moving down a little faster. Sorry, what? 6, 3, 6 seconds. and then plug that in, and you get to. Oh, okay. 0.79, but didn't we get 0.743 for part A? Yeah. Okay, 0.797. Oh, whoa. Because it's not going faster. It's going, we don't know what it's doing. So it turns out it's going slower. So it does take a little more time. Okay, sorry, I'm all mixed up on this problem. So and then that gives you that V is equal to, I think it's 6.36. If you plug, you can plug it back into any one of these equations. Uh, V is equal to 5.076 times 0.79. No, divided by 0.79. 6.37 or something. So to make it go exactly 5 meters horizontally, you have to throw it 6.37 meters per second. Okay, well, two things. I made that problem look harder than I had to. That's for sure. It's not as hard as I made it look, but it is harder than I meant it to be. So sorry about that. Any other questions about the test? Might as well do 4. Anybody want to see 4? We've done everything else. Okay, so for 4, a ball rolls off the edge of a table. And it lands at a known spot. There's not really any reason that I have to draw the cup there. I think I probably just figured out how to do that in Word or something. And its starting speed is 10 meters per second. And the height is 1 meter. And we want to calculate this horizontal distance that it travels. So time equals 0 is going to be when it leaves the table. Time final is when it hits the ground. The coordinate system I'm going to put on the ground right beneath where it leaves the table. And then the initial velocity, this is sort of the one thing that you have to infer from what's written, is at the instant it leaves the table, since it's been rolling along the table, it's moving exactly horizontally. So the initial velocity vector is 10 meters per second in the positive x direction and 0 in the y direction. Okay, so we don't know time final. It's a free fall problem, so the acceleration is 0, negative 9.81. The initial position is 0, 1. The final position, you could say that we know PF y, that's 0 because it lands on the ground, and we want to find pfx. The initial velocity is 10, 0, and we don't know the final velocity. And so the way you have to solve this, I think, is a way that's pretty common in these two-dimensional problems. There's no equation that gives us this right away. So we have to start by finding TF and then plug that, and we'll use the y equation to find TF and then plug that into an x equation. So PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0 is equal to 1 plus, and people who made mistakes on this was a place where a lot of people made their mistakes. I guess it just comes from not inferring from what was happening in the problem that this thing was moving horizontally. So then I saw a few different versions of components for that initial velocity, but this should be 0 here, because it's moving horizontally. There's no vertical component. So plus 0 minus 4.905 TF squared. And so TF squared is 1 over 4.905. And then TF is like 0.452. And then once you have the time, then you can use the x equation to solve for PFX. So PFX is equal to PIX plus VIX TF plus this stuff. That stuff isn't going to matter because there's no x component of the acceleration. So PFX is equal to 0 plus 10 times 0.452. And so it's equal to 4.52 meters. Any questions about that one? All right. Anybody have any homework questions? Okay, so let's go back to, so we're going back to kinetics. And remember that, so we're talking about all the different types of forces that can be applied. And so I broke up forces into two sort of big categories. Force is either applied by an object's weight or it's applied by contact forces. And the contact forces are pushing forces. And if an object is pushing on the boundary of the chosen object, that force is toward the chosen object, perpendicular to the surface. The second type is a pulling contact. And now we're done talking about both of those. And the last one is friction. So that's the last type of force that we have to talk about. So friction force. And friction force is a force parallel to the surface that resists sliding. Well, there are a whole bunch of different kinds of friction, like you can have friction in rolling and, friction in the bearings of wheels and rolling resistance. But there's all these different types. But the only kind we're going to talk about is a friction between two dry objects that are just sliding relative to each other. And friction, we can break this up into two different types. One is static friction. And static friction, if two objects are at rest relative to each other, so if they're not sliding visibly relative to each other, static friction is what keeps them from starting to slide. I'll show you what I mean. So it keeps objects from starting to slide. And then the other one is called kinetic friction. And that's a force between two objects that are moving relative to each other. They are sliding. Let's say in a sliding motion. Okay, so here's the idea of static friction. So this table. So right now, if you think about the forces that are acting on this table, there's a weight force down, and there's a normal force pushing up that counteracts the weight. And that makes sense. It's not moving. There's no horizontal acceleration because all the forces are just vertical and they just counteract each other. But now if I push a little bit on it, not enough to make it start to move, but I'm putting a horizontal force on it. Now if you think about the free body diagram, there's a weight force down, there's a normal force up, there's a horizontal force that I'm applying to it, I'm pushing it that way. And so if those were all the forces acting on it, it would have to start to accelerate that way because there's no horizontal force counteracting the force I'm applying. For it to have zero acceleration, the horizontal forces have to be zero, and I'm applying a force this way. Okay, yeah. And so the only way that it can stay at rest is if the rug is applying a horizontal force in the opposite direction that I'm pushing. Here's the sort of funny thing about it is if I push a little bit, just a tiny little bit, the rug isn't pushing very hard back, But if I put a bigger force into it, the rug just always applies whatever force is necessary to counteract the force I put into it until I get up to a big enough force that it starts to move. And then once that happens, then we're in kinetic friction. Okay, so that's what static friction is. It's just there's a resistance to motion that applies whatever force is necessary to keep the thing from moving until you get to the maximum force it can apply, and then it starts to move. Well, static friction we're not going to do calculations with that. Yes. Yes, it's always parallel to whatever surface the thing is sliding. Because what? Yeah. So yeah, let me just draw a free body diagram really quick. So in that case, what was going on was um, there's a weight force, there's a normal force, there's the force over here. Uh, I'll call that F. That's the force my hands are applying. And then the friction is applying equal and opposite force to counteract that F. Okay, so the static friction we're ignoring, but the kinetic friction, so that's the calculations we're going to do are when things are in motion. We'll only do these. And not like really harder or anything to do static friction problems. We're just going to do one of these. And really the technique is fairly similar. It's just sort of a different way to think about it, but we're only going to do these just in the interest of time. Okay, so kinetic friction. Okay, so to define a force, um, you need to give a force as a vector. So you can define it as a magnitude of the force and a direction. And so that's how I'm going to define this. Um, so first, the direction is opposite the direction of motion. And the magnitude of, so I'll call that F sub F for force of friction. That's equal to this constant mu uh, times the normal force. Um, where this constant mu is called the coefficient of kinetic friction. Greek letter mu is the easiest Greek letter to remember because it's like exactly in between a M and a U, and that's how you spell mu. So now you'll never forget that. Okay. So one thing to, so as far as like understanding friction forces, uh, up until now, like we've done some problems with things rolling and sliding along surfaces with no friction. And remember, this even came up, like a couple people asked questions about this. It didn't matter which direction the object was moving. I didn't have to specify, like, imagine like the one with the cart rolling up or down the incline. I didn't have to specify that the cart was at that instant rolling up the ramp or down the ramp because the acceleration was the same no matter what. You remember that? Um, but now that the direction is opposite the direction of motion, we have to know the direction that it's moving because that changes what the force is doing. You know, if an object's moving this way, sliding this way, the friction force is going this way. And if the object's moving this way, the friction force is that way. And then the second thing about this is that the magnitude of the force depends on how hard the two objects are being mashed together. That's what the normal force is a measure of. And that makes sense, it's pretty easy for me to slide this table. But if there were 500 pounds of weights on top, it would be a lot harder for me to slide it. So the harder you push those two things together, the bigger that friction force is. And that sort of makes sense with intuition. Yep. That's a good question. There can actually, most of the time, there's also going to be pulling or pushing or something. But there can be sliding friction without forces applied, because in order for there to be sliding friction, the thing just has to be sliding, And what its velocity is at a given instant, doesn't have to do with the forces that are applied at that instant. It has to do with all the forces that were applied leading up to that, So like if I don't know, with a golf cart or something, got this thing, well, imagine it's not on the rug. It's easier to imagine if you imagine it in the hall or something. But so you got this going 15 miles an hour, and then stop the golf cart. And for at least a couple seconds after, it's going to be sliding down the hall. And so in that case, there would be no pushing or pulling forces on it. But it would have a velocity, and so it would have kinetic friction just because of the forces that had been applied before. So, and if you think about it, I think that the difference between what's happening at a single instant, like the forces and accelerations at a single instant, and the velocity that just depends on the forces and accelerations up until that instant, that's kind of an important idea with this, because Newton's second law, yeah, you'd think maybe off the top of your head, you'd think the velocity of an object has something to do with the forces or whatever, but Newton's second law says it doesn't. The velocity is totally unrelated to the forces that are being applied. That's So I'm just going to start out with an example and then go into some more complicated examples. Okay, so let's say this object is sliding along a horizontal surface, and it has a mass of 10 kilograms. And there's a force of 30 newtons applied to the right. And the direction of motion is this way. And we'll say that the coefficient of kinetic friction is 0.2. And by the way, that coefficient of kinetic friction doesn't have any units. So that's probably worth writing up here. It's just a number. Okay, so that arrow showing the direction of motion, that could also be written as that's the direction of the velocity vector. Those mean the same thing. The direction of the velocity vector is the direction that the object is moving. So you might see either one of those in problems. But now this is the first time that I've had to show anything about the direction that the object's moving in order to do the calculation. If everything else was the same, but the direction of motion was the opposite way, we'd get a different answer for the acceleration. And that hasn't been the case up until now. Okay, so let's calculate what's the acceleration? Okay, so I'm going to start with a free body diagram of the box. There's a weight force of 10 kilograms times 9.81, so 98.1 newtons. And now going around the boundary, there's the 30 Newton force. And then the ground is still pushing up on the box, so there's still a normal force. And which direction does the friction force point? To the right, correct. So it's opposite the direction of motion, so it points this way, and it doesn't matter where you draw it. I mean, I could have drawn that arrow over on the left side, and it still means the same thing. So I'm just drawing it wherever it looks less cluttered. And the magnitude is the coefficient of friction, which was given in this problem as 0.2, times that normal force. Okay, so now go to Newton's second law. You have a 30 Newton force in the, oh, one thing I didn't say this, but so remember in rolling and sliding problems, we're always going to choose a coordinate system with the y-axis right out of the surface and the x-axis horizontal. We talked about that last time. In this case, with any horizontal surface, that just gives us the coordinate system that we're used to. But if there's an incline or anything, we're going to use a weird coordinate system. This one is what we're used to. Okay, so the 30 Newton force is in the positive x direction, so that's 30, 0. The weight force is in the negative y direction, so 0, negative 98.1. The normal force is in the positive y direction, so 0n. The friction force is in the positive x direction, so 0.2n, 0. And all that's equal to the mass of the object times the acceleration. What do we know about the acceleration? That's right. So we know it's in the x direction, so I'm going to write that as a0. So all we want is that value for a, because we're trying to calculate the acceleration vector. This is the acceleration vector. We just need to know what a value to fill in there. So normally, up until now, we would just use the x equation alone, but we can't do that here because we have a second unknown. So what we're going to do, and this is pretty much how it's going to go with every friction problem, use the y equation to solve for n, plug that n value in there and solve for a. In this case, it is, but not always. Okay, so the y equation says 0 minus 98.1 plus n plus 0 is equal to 0. And so n is equal to positive 98.1. And then the x equation says 30 plus 0 plus 0 plus 0.2 times 98.1. I'm substituting that value in for the n, is equal to 10a. And so that says 30 plus 19.62 is equal to 10a. So 49.62 is equal to 10a. So a is equal to 4.962 meters per second squared. And so then plug that back into the acceleration vector, and you get 4.9620, or that's in the positive x direction. So this way with a magnitude of 4.962 meters per second squared. Okay, so now, since this is the first kind of problem where to solve the problem you have to be given the direction of the velocity, we have, since we know the direction of the velocity, we have enough information to know whether it's speeding up or slowing down or neither. So let's think about that. Okay, so our acceleration vector is to the right. The motion is to the left. So in this case, that 30 Newton force and the friction are slowing that object down. Any questions about that? Okay, I think let's just do the quiz. So it's Veterans Day on Monday, so school isn't open. And so we don't have class Monday, and that also means that we're not doing any lab next week. And then I think the week after that is Thanksgiving week, and we're not doing lab that week, and we don't have class on Wednesday. So the next 4 classes that we would have, we only have 2 of those. And we don't have labs either of those 2 weeks. So sorry. But I mean, you can always go on D2L and read about the old labs if you miss it.